Okay, I'm back. My batteries ran out and I probably have like 5 minutes or less left. So I was talking about how we find a makeshift t-value. This t-value is the weighted average, and it depends upon the expected variance of the population given the variance, I'm sorry, no, I take that back. The expected variance for an average given what we have for the variance here. For the actual sample size, it's larger. We get the variance of our individual sample, but for the average, we're looking at the variance of individual values that we get already, and we're assuming that's representative of the actual population. So we could try to kind of divide that value by n for our sample to figure out what the variance of our actual averages for our sample, for example, for each of these that we're finding the confidence interval for the difference of, for the actual populations. So we take that variance for sample 1, divide it by the number in sample 1, take it times t for that 1, and then we add that to the other t value. We're going to basically divide that out. We're going to see basically what the average is between these two, but that average is going to be skewed by which of these values is higher, because these are kind of coefficients for this. So when we do that, because for this one we're taking the variance divided by 2. Again, now you got to figure, in this case, n is going to matter a lot. So with a small number, it's going to be a larger number. We're going to go with whatever t1 is, which is going to actually be dependent upon n. But we're basically saying, if this isn't we're not confident about this really, we're going to look at whatever this n is, because it's probably dependent upon n. But if they're so close together here that the variance is really low, then maybe we can just look at the other n, basically, for degrees of freedom, more than the other one. But we're still considering both of them. We're finding a weighted average depending on these values. And then we're dividing by their variances divided by their respective n's, their respective variances divided by their respective n's, kind of like we did up here, but we used the number instead, but now we're using the variances. We don't know that, we're assuming the variances are different here. So we still got to come up with one t value, and t depends upon n. We could even have different n values here, right? But we got to find some value that we're going to say our reliability coefficient. So how many standard deviations do we want to look at for just basically for our level of confidence? Then we make our standard deviation, we come up with a standard deviation by adding the variances of them, but we don't use a pooled value here because we're not assuming they're the same. We're just assuming that they're what they are. So we take each variance divided by their respective n to find the variance of that average, right? And then we add to the other one and to try to find the variance of that population's average given just a sample of that number. We take that, we take the square root of that to get the standard deviation. We take that times our reliability coefficient, which is the number of standard deviations that we should use for that level of confidence, which we pick 95% as. And then we take plus or minus the actual differences of the averages for those two samples, and that gives us our confidence interval. Now, I just didn't have a lot of room on the board to give you examples, but in the future I do plan to also work out some problems. I hope you enjoyed this. Thank you.